Hey there, everyone. My name is Ryan. Welcome to my analytics channel. So, in the narrative today, I want to talk about retail return fraud detection and behavioral sequences. We're going to use graph analytics to go ahead and understand the relationships and the connections between potential fraud rings that consist of a bunch of people that commit retail fraud. They buy things and they return to a store using a variety of different techniques or different like little cheating methodologies, I'll call it, whatever you want to call it, right? Basically, common retail return includes return short-term returns. You borrow something or you buy something, right? Wear it once, maybe twice, return it, right? So you're using the item for free. That's not fair to the retailer. Wardrobe buying, high-value items, wear them, use them, return them, maybe even return similar but slightly different items, right? Maybe you return a item that's cheaper, or I mean, you buy an item that's cheaper, and return a higher cost item, or vice versa. There's different ways of doing that. I mean, if you do it the wrong way, you kind of screw yourself. But there's a couple different ways to kind of like cheat the system, right, and get your money back for something that you're not fully entitled to. No receipt and full return abuse, that's pretty common, right? You say, oh, I got this as a gift, I don't have the receipt, or I lost the receipt, and you expect a full refund for something. Maybe you bought it on sale, the sale's over, it goes back to the full price, and you return it at the full price cost, something like that. Credit card was not present, lost or stolen credit cards, friendly fraud like chargebacks, buyer disputes after the bank has paid, all kinds of refund laundering, gift card laundering, right? Stealing gift cards. I've heard this actually activating the gift card when you haven't paid for it. You stole it, right? It's basically free in the store. It has to be activated. I guess people can activate these off-site outside of the retail outlet, and once the car is activated, you can buy whatever you want, right? There's policy gaming, promotion abuse, employee collusion, right? It could come from the inside. The theft can actually come from inside the retail outlet. Triangulation, whereby marketplace fraud is created by fraudsters listing items on different marketplaces, using stolen cards to buy items, ship them to a buyer, and then the buyer returns that to a different merchant in a different location for a full refund. There's all kinds of crazy things, right? So I came across this recently. I put together some sample code here. Let me show you my findings. I think this is pretty interesting. So we're going to import the typical Python libraries over here. I am going to create some synthetic data. Now, I don't have actual fraud-related data, data related to retail sales that consists of fraudulent transactions, right? To get my hands on that would be very difficult, right? And I'm sure it exists. I'm sure some retailers have this data, but that is personal and confidential. They keep that close to the vest. I don't have access to that, right? But I'm going to simulate data that should represent pretty accurately what this fraud data would look like if we did have it. Again, I don't have this. I don't work in the retail business, but I'm showing you, if you are a retailer, how you can use your actual retail data to try to discover these fraudulent activities and protect yourself from these scammers, right? So I'm going to go ahead and run this, create the synthetic data, and I have all the data related to retail transactions and whether or not the event is considered fraud or not fraud. So we have the transaction event type, customer ID, item ID, things like this, store ID, channel. Was this a web app? Was this in store? Was this purchased on a cell phone, something like that, right? On a laptop or something? Receipt was present, yes or no? The reason code, policy version, and is this considered fraud or not? That is what we're trying to determine, right? So the fraud is going to be the target variable. That is the dependent variable, which is dependent on all these other variables. Now, not the customer ID or where I just saw this over here, or the um, item ID could be relevant. The customer ID doesn't matter. In most of these scenarios, the ID doesn't matter what you're doing. If this is a retail transaction, then you would look at the SKU number because that would identify the item being sold. So this ID would be relevant most of the time in the ML world, which is short for machine learning or data science or deep learning or AI. IDs don't matter whatsoever, okay? You don't care who that is. but in some cases they actually do. So I don't care about the customer. I don't care about the store ID too much. I mean, maybe if there's high frequency fraud at one store, I might want to be aware of that. But again, IDs don't deliver a ton of information. What is more important is things like this: event type, um, address of the store, right? If there's some geographical location that's getting attacked by these fraudsters, we do want to know about that. The channel would be important. Is the receipt present or not? And it is fraud. That's the most important thing that we're trying to test for here, right? So the event type could be purchase or return. If it's a purchase, that's not really fraud unless somebody was using a stolen credit card or what is it called? Like a gift card that was never paid for that has been activated once you're outside the retail outlet. So purchases could still be considered fraud, right? You could have a stolen credit card, go to make a purchase, walk out the store, it looks totally legit, but if that's not your credit card associated with yourself and your bank account, that's fraud. Most of the time, though, fraud consists of returns, right? Returning the wrong item, returning a more expensive item when you purchase a cheaper item, things like this, right? Um, just buying an item, wearing it a couple of times, returning that so you get to use the item for free. That's a big no-no, right? You should not be doing that, but people do that nevertheless, right? So sometimes the price, if it's an expensive item, it could trigger people to engage in fraudulent activities, right? If it's a small item, $5 or $10, who really cares, right? Are you really going to commit fraud for a like a container of bubble gum? Probably not, right? But if the item was worth thousands of dollars, that's probably more likely target for fraud. So the price could be somewhat of a trigger for fraudulent activity versus non-fraudulent. So let me run this next script down here in the next cell. So we're looking at is return, customer lag hours, and customer 7-day event. So this is a 7-day lag, lag hours in terms of was purchase done in the morning and then the item is being returned in the afternoon. If it's pretty quick, probably the person used their credit card, maybe even a friend or family member credit card, use the item or switch the item most likely and return it in the afternoon. So you get your money back, you get a full refund, but now you have a more expensive item, right? And you're returning a cheaper item, right? But getting the value for the more expensive item. So the lag hours is important. The number of events in the last 7 days is important, right? So these fraudsters tend to do these things in quick bursts. They do them in cycles. If there's a bunch of returns in the past 7 days, that could be a fraud flag. In the last 30 days, that could be a fraud flag. And customer return ratio, if the customer is returning a lot of things, like 50% or more of the items purchased are actually returned, that could be a flag as well, okay? So normally customers are not going to purchase something and wait a couple of months because the opportunity to make the return is probably going to be invalid at that point, right? You're probably going to exceed the point where you can make the return. A lot of these are 7 days, maybe 2 weeks, maybe 30 days. Then they won't even take the receipt, even with the item in the receipt. The store probably won't take the return, right? So it encourages people to do fraud quicker and in shorter time intervals, right? 7 days, 30 days, high frequency returns, lots of returns in a short period of time. So that's what we're looking at here. So in the last data frame, we ended up with policy, version, and is fraud. So we're adding a few new features to the data frame now. Our DOW is day of week and weekend, and deviation based on lag hours. Okay, so this could be a trigger of fraud or an indicator of fraud too, right? So we have, let's see, is return, is fraud, policy version is fraud. So the last data frame ended with these two, right? Policy version is fraud, right? That was the original data frame. Now I'm doing feature engineering to create some new features from the already existing features. So is this a return, yes or no? Customer lag hours, customer lag 7 days. Was this purchase done within the past 7 days? 30-day returns, 30-day return ratio. If it's a higher ratio, more of a flag for fraud. Pair lag days, hour, day of week. So Monday, Tuesday, Wednesday, things like this, Saturday, Sunday. Is this a weekend? Yes or no? Lag hours, and then no receipt. No receipt, you want full return. That's a huge red flag. So let me go ahead and run this next script, and I'm going to give you all this source code. Okay, so you have everything you need. Copy and paste it into your own Jupyter notebook environment. Run it. I'm giving you everything you need. I'm not going to spend a ton of time on like all the nuances of what all this code does. Some of this stuff I find on Google. If I get into a tight pinch and some um, I'm getting a dictionary, it's coming back, and it needs to be converted to a list or vice versa, things like that. Sometimes I'll go into Chat GPT and say, well, I have this error issue. Can you help me straighten it out? So a lot of these things, you have to know, you learn, you Google it, ask Chat GPT. I'm not going to go into all the details of everything because the video would drag on and on and on and be never ending. But I will give you all the code and you can figure it out for yourself. And I have a bunch of notes in here too, which are good guidelines that's going to help you understand what's going on line by line of code here. So I will just mention this. I created a UDF. This is a user-defined function to go ahead and look at customer IDs, shipping addresses, and look at all the relationships between all these different transactions to try to understand, like basically who's committing the fraud. Is this fraud perpetuated by a ring of fraudsters? Are there other people associated with this one person? Is this a lone wolf? How do all these fraud transactions interact or connect with each other, right? So you can think of a graph analysis as, or a graph relationship or graph analysis as your friends on Facebook. Who are your friends? Who are your friends' friends? Who are your friends' friends' friends, right? And how do you fit into that picture? So your friends with your friends' friends' friends, maybe, but not necessarily. How is that connection made? That's what graph analysis helps us to flesh out. Okay, so we did the analysis using a graph technique. Now we have, let me see over here, we ended up with deviation lag hours and no receipt. So we should start down here, deviation lag hours, no receipt. Great. So now doing a graph analysis, we have a couple more feature engineering items that we just created and appended onto the end of the original data frame. Remember, the original data frame ended with policy version is fraud. I created a few very generic types of feature engineering exercises, right? And we ended up with deviation lag hours and no receipt. That's exactly what we see over here, right? So we go down here and continue with analysis by adding in a couple more features onto the same data frame, appending over to the right. We have customer, degree, deviation degree, address. So these are different degrees or different relationships for all these different people that are making purchase transactions and return transactions, right? And we're trying to understand all these relationships. So it is pretty complex, but using graph analysis, we can expose the complexity and try to understand the details of what's going on underneath the hood here. So we have customer lag hours. This is the time since the customer's previous event. Last 7 days, this is rolling days. Last 30 days rolling. Pair lag days, this is the days between consecutive events. So customer returning multiple items, customer returning the same item multiple times, things like that. That is definitely a red flag. Time since previous event on the same device. Okay, so you can make returns and even get pay and get a refund on your phone, right? So if you get multiple refunds on the same device, either through a web browser, maybe on Amazon, maybe on Walmart, Costco, something like that. You're buying these things, you're making returns. We could also measure the device and try to understand, how many returns are being pushed back to the same device. That would be a red flag. If there's dozens and dozens, that would seem very unusual, very unique, right? Okay, so continuing on, let me run the code in this cell. Okay, script runs pretty fast. Now we have event time ID, item ID, lag in terms of days. So this is a 1 day lag. So these people waited 1 full day to make the return. This is less than a day. The transaction was done probably in the morning. Return was done late in the afternoon or early afternoon. Purchase and return was done just before the store closes. Okay. Receipt, no receipt. No receipt, that's a red flag. People are saying, hey, this was a gift, or I lost the receipt. That's their excuse. If you don't have a receipt, maybe the item was shoplifted, right? Several $100 item, maybe a couple $1,000 item was shoplifted. Now you take it back to store, you want a full refund in cash. Very suspicious, right? Very, very sus. My son and his friend call it sus, short for suspicious. Sus, suspicious, you can use whatever you want. So refund amount, and then is fraud. The bigger the amount, Probably the more fraudulent the activity. Again, somebody is not going to return a $5 item probably and expect a full return. If you buy, like, I don't know, a bag of gummy bears or something, you're probably just going to eat it. You're not going to like open the gummy bears. Who knows what these people are even capable of? Open the gummy bears, stick in some pretzels or something and try to return it. I don't know. Like, there's some crazy guys out there, right? So the higher the item, the more likely to fraud. The lower the cost, the less likely to fraud. Control Enter to run this. Again, we get the data frame with all of the relevant features over here. This can help us detect what activities are fraud versus non-fraud. Now we want to look at suspicious devices or suspicious addresses. Okay, now again, the device can be a phone, laptop, what else? Desktop, something like that, something that you're making transactions over the web, or your phone. You can pay with the phone. You can get not receipts. You can get refunds with your phone. All right, so we're looking at the device ID and trying to determine, can we make deterministic decisions about whether or not something is fraudulent based on the type of device. Okay, so we're going to look at that as well. Maybe we can, maybe we can't. Control Enter to run this. Now we're looking at group by the comp ID, and we're looking at again the time of the transaction, customer ID, device, ship address, so on and so forth. And is this fraud or not, right? So we're collecting all this information. We're going to try to make sense of it and distill this into a decision-making tool to help us understand what is fraud and what is not fraud, right? And we can implement a real-time system at the point of sale, POS, where the retail transaction is occurring in the store. And if a person brings something back, make sure this system is running in real time. You could use Kafka, you could use Azure, AWS, GCP, some type of cloud-based tool to scan the code on the receipt, right? And when the person is making a return action, instantly it goes to the cloud provider or Kafka. If you have maybe a local on-prem system, it's recognized immediately and it's being flagged as potential fraud, most likely not fraud, right? So that is the goal here, to look at all these different data points, all these different potential triggers or flags for fraud, and try to determine, is this a legit transaction? We want to create goodwill with the customer and keep them happy. And the old saying, the customer is always right. If they want a legitimate refund for a legitimate transaction, by all means do that, right? We're trying to identify fraud and prevent that from happening. So we're collecting all these data points, collating them together or commingling them together, whatever you want to call it, and then trying to determine what's fraud. So here in this case, is fraud, is not fraud. So we have a fairly balanced data set. So a lot of times in fraudulent activities, you'll see highly imbalanced data. You'll see most of the transactions are not fraudulent. You can imagine a credit card being swiped probably 99.9% of the time, maybe even more. Credit card swipes are totally legit. Once in a while, there is fraud. Either the card is stolen, maybe somebody, I don't even know what it's called, but you can actually like activate cards that have been deactivated. I think there's a way to do this, and it looks like a legitimate transaction, but it's actually not, right? That would be a fraud event, things like that. But those are pretty rare, right? In this case, we can look at is fraud or is not fraud, Control Enter, and we see that it's kind of well balanced. So again, in a lot of cases, fraud is pretty rare, right? Probably 99.9% of the time it's legit. Maybe 0.01% of the time it's going to be a fraud transaction, right? So it's hard for the machine to learn when most of the events that it sees are non-fraud transactions. All of a sudden, the fraud transaction pops up, but the computer says, well, I haven't really seen this before. I've only seen this in a couple isolated incidents. So it's hard for the computer to determine this is a fraudulent activity because it's so rare. It can't build up a whole corpus or a whole foundation of what is fraud, because all it basically knows is non-fraud, right? You see one or two events that deviate, and it's hard for the machine to learn this is fraud, right? So in this case, it's a little different, but the reason for that is because we're looking at parallel days, and the color is fraud, either 0 or 1, right? 1 is fraud, 0 is not fraud, and we can click on these and we can turn them on or turn them off. But basically, we're looking at um, basically, these fraud transactions based on returns, right? So a lot of times returns could be considered fraudulent. So most of the returns, I'm sorry, most of the transactions are not fraudulent, but if people bring back a whole bunch of returns, that is going to be like more of a higher awareness of fraudulent activity. Okay, so you have to understand the scenario, the context that we're working in, and things like that. So a lot of times these returns are actually fraud. Sometimes they're legit. That's why we're getting kind of a balanced data set over here. Okay. So moving on here, let's look at a couple more graphs. So I put this together to try to illustrate the point. I always say a picture is worth 1,000 words. Let me hit Control Enter to run this. So in terms of overall purchases, we have 82.3 thousand purchases is fraud, 0. So if a person makes a transaction, just buys the thing, walks out the store. Now they could have used a stolen credit card. This is kind of rare. Most of the purchases with no returns, totally fine. Just let it go. You made a normal transaction and business as usual. But you can see down here, when you get into returns, the returns, now you have 1,234 returns, and they're all fraud, right? Over here, you have 830 returns, and these are not fraud, right? I did that wrong. So we have 1, 2, 3, 4, and what is this? What is this thing? 830. 1, 2, 3, 4, and 830. Let me look at this right here. So this is very interesting. 1, 2, 3, 4, 830. Okay. So 1, 2. Whoops. 830, right? 830. Okay. And this is fraud. Okay. Equals. So we have 2064 transactions. 59% are fraud, and 40% are not fraud. Okay, so this is very interesting. So we have 1, 2, 3, 4 fraud cases among the returns, 830 non-fraud. So these are legit returns. The person just changed their mind for whatever reason. They want their money back. These are fraud transactions, right? They're returning a different item, or they bought a more expensive item, right? Return a cheaper item, but they're going to get the full price for the expensive item. So the person's actually making a profit on this. 59% is fraud, 40% is non-fraud. That corresponds to what we see over here. Fraud, not fraud. 1 is fraud, 0 is not fraud, so that matches exactly. And we have 2,064 returns. So you can see 60% of the returns are fraud, 40% are not. When you look at just purchases, there's no fraud over here. Purchase has been made. The person completed the transaction. They got the item, whatever it is, and they left the store. The store made the money. The person's happy. They got what they wanted. Over here, returns, 60% of the time, it's a fraud transaction, right? So you have to consider the context and the overall like scenario that we're operating in. If it's a return, it's going to be suspicious. Just purchase, leave the store. There's no suspicion whatsoever. So over here, return type, event level, return. Yeah, 60% of the time fraud. Purchases, 0% fraud. Okay. So returns with a short latency or no receipt, Control Enter to run. So less than 3 days could be fraud. 58% of the time this is fraud. 61% of the time the fraudster waits between 4 and 7 days. There is almost no fraud if the person waits 8 to 14 days, 15 to 30 days, or greater than 30 days. So there's a few reasons for that. The person wants their money back sooner. They don't want to wait more than a week to get their money back. They're going to get it back or attempt to get it back in less than 3 days or 4 to 7 days. They're not going to sit on this, right, and just wait for time to pass and then take it back to the store. And the company could have a policy like all returns guaranteed within 2 weeks or within 1 week. If you want to make a return, bring it back within 1 week. Otherwise, we're not going to talk to you, right? So person wants the money back faster, or the return window closes and you just can't do it. So return fraud by receipt presence. No receipt, 63% of the time it's fraud, right? You're telling the person it's a gift, the cashier it's a gift, or I lost a receipt. If there's a receipt, 58% of the time there is a fraud case here, right? So buy something more expensive, return something cheaper, and you get the money back for the more expensive item because the receipt is associated with the more expensive item. So you're making a profit at the expense of the retailer, okay? So that's a big no, 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 don't do that. So returns fraud rate by refund type, partial refund, 59% of the time is fraud, 59% of the time full refund. Okay, so it's pretty even breakdown. Return fraud by refund amount, less than $50. This could be considered fraud. Honestly, like I personally wouldn't get involved for any kind of fraud, period. But for less than $50, is it really worth it, guys? And I don't think so. If you're if you have $50 to $100 at stake here, actually slightly lower risk of fraud, 59%. This is 61%. His 58%, 150 to 250, 59%. Greater than 250, no fraud. So that's a little surprising to me. I thought the higher the amount, there would be more fraud, but maybe what's happening is retailers would be more suspicious and more hesitant and very reluctant to give back a refund more than 250. So the fraudsters know this, and they're not even going to bother with these high ticket items, but they're going to concentrate on these lower cost items over here and just do this over and over and over and over, right? If you do less than $50 5 times, that's equal to 250, and the retailer might not even suspect that. They're thinking, well, less than $50 is $49.99, probably not fraud. But if you do this at 5 different stores, and you'll see in a few minutes, if you have a network of fraudsters and you can do handoffs to other fraudsters and they can go to these stores, other people go to different stores in the neighborhood, you can do a lot of returns very quickly. Each item is less than $50. It can get up to 250 in fraudulent activities very quick. Okay, control enter time of day, or I'm sorry, the type of device that you were doing the transaction with, the purchase and the refund transaction. So this is app, a phone, most likely, right? A store, in-person retail, purchase and refund. And on the web, this could be Amazon, Costco, Walmart, whatever the case. Probably Amazon would be the big one. Fraud rate by hour of the day. So again, this was a little bit surprising. I thought it'd be a little more consistent, or maybe like early in the morning, later in the afternoon. But this really bounces all over the place. So there's no pattern whatsoever based on the time of the day when fraud will occur. So it seems to be kind of a dip over here, 1700 hours. So was at 5 p.m., right? Not a lot of fraud, 1% of the fraud. It seems to be kind of a peak over here, but all of these are small. These go from 0.01 to 0.018, so they're all pretty small fraudulent transactions, and the line bounces around a lot. So it's interesting to see this. I thought there'd be more of a pattern. There's really no pattern, nothing to exploit here. So I would say you can't really say more fraud occurs at a certain time of day or it doesn't occur at a certain time of day. It's all over the place. But again, these numbers are pretty small, so it's really de minimis. I wouldn't spend too much time on that. So this is fraud rate by hour and day of the week. So you have the days of the week on the y-axis on the side. The x-axis has the 24 hours. So the darker the color, the more likely the fraud. As you can see, there is some fraud occurring Wednesday at 10 p.m., close to 100%. It's kind of interesting, right? Because over here, we didn't really see that kind of pattern. That's okay. That's why we have to look at different charts and different angles, right? We have to look at this from different perspectives. There's some fraud over here, 84% fraud at 5 o'clock in the morning. So that's kind of interesting, right? People are out and about at 5 o'clock in the morning on a Sunday. So that is kind of interesting, right? I don't think these are people heading off to church, to say their prayers and to sing their hymns. Probably, people's guards are down at 5 o'clock in the morning. Maybe there's one cashier working the register at some 24-hour shop. Who even knows what this is? But apparently they're open, and there's fraud committed in terms of, returning things without a receipt or returning a different item, less expensive market value than the item that you purchased, and you're getting the full refund for the higher amount. So over here, Wednesday, 4 o'clock in the morning, pretty low fraud. I wouldn't expect too many people to be out in the 1 o'clock in the morning. Oh, what is this? 1 a.m. on a Tuesday, not a whole lot of fraud, but there's still fraud here. There's still fraud all over the place, right? You don't see anything with no fraud, 25% chance. And this is a probability too, by the way, okay? I'm not saying like 25% of the items returned on a Monday at 6 p.m. is going to be fraud items, but there's a 25% chance that it could be. Okay, so what else do we have here? So higher risk overnight, 0 to 6. Maybe people are tired at the cash register, the guard is down. Evenings, 1800 hours, so it's 6 p.m. to 11 p.m. Slight bump up there in terms of hours. Increase on weekends, Fridays and Saturdays, when staff return verification might be weaker. Okay, so that there's kind of a pattern here that we can exploit and detect, and make sure that the retailer is on guard, right? And make sure that they're trained and they're aware of this. And if somebody comes into the store between midnight and 6 a.m. asking for refunds, validate that. Make sure it's legit. Evenings, 8 p.m. 6 p.m. to 11 p.m. Potential for higher fraud during these hours. So be vigilant. And weekends, Friday, Saturday, Sunday. Okay, be aware of that. So I'm going to go ahead and create another analysis here. So looking at score returns and different types of return events. Okay, so I'm going to go ahead and hit Control Enter to refresh this. We are going to look at feature importances and see what types of different features have the most statistical significant impact on determining whether or not something is fraud. So this is kind of a machine learning exercise. I've done this in some of my other videos, basically looking at all the different predictors of fraud, all the different features that we saw in that data frame before, and see what different features have the most probability or most statistical likelihood to be associated with fraud. So let's let this run and we'll see what the ML model spits out. I'm not going to go into all the details. I have several videos on my channel about how all this stuff works, feature importance. I have a handful of videos specifically about this, and I've introduced this topic in some of my other videos as a corollary, not as the focus of the video, but introduced this topic many times. So I'm using a gradient boosting classifier to determine the outcome. Is this fraud or not fraud, right? It's a binary outcome. Any kind of classifier is binary. Yes, no, true, false, on, off, 0, 1 outcome, right? So we're trying to determine the potential here for fraud, and the refund amount predominantly determines is this fraud or not. So the customer returning items within 30 days really doesn't have any impact on fraud. 2% price doesn't. I thought price would be a little bit higher. Actually, whether or not something is returned within 30 days is more indicative of fraud than price. Hour of the day, not really. All these other things like here, day of the week, lag days, customer returns within 30 days has a 1% impact on the probability of fraud. Customer return ratio, which means how many returns is the customer doing within 30 days. So is a return done within 30 days is different from multiple returns in 30 days. And then returns within 7 days has a small but very weak impact on fraud, 1%. So what really drives fraud is the refund amount, right? So I guess price and refund amount should be kind of highly correlated, but maybe not, because the fraudster might not be too concerned about the original price, but they are very self-aware of the refund amount. So again, in this scenario, I don't know exactly because the data doesn't really explain this. We could do more of a causal inference. I have a video on my channel about how causal inferences work. You can dig into this and see why this happened. I would suspect, without doing the experiment and knowing 100% certainty, the refund amount is the most important, because that's what the fraudster is getting back. And I would guess they maybe buy an item cheap, right? Then what would they do? Buy a second item more expensive and then return the cheaper item for the with the more expensive receipt. I'm trying to think, like, I think that's how the scam would work. I don't know if I said that exactly right, and I'm not a fraudster, so I don't know all the angles these guys go through, but probably something like that. You'd probably buy two items, one cheap, one expensive, and return the cheaper item with the more expensive receipt. I think that's what we're seeing here. Okay, I'm just guessing, but that would make sense to me. So I think that makes sense. So gradient boosting is a way to run these models, right? A booster will take an ensemble method and apply a bunch of ML techniques to try to solve the problem. It'll take the best output from that model and run that through another ensemble method. So it does another iteration of testing, training of the models, takes the output of that, boosts that to another level, right? A little bit different from a bagger. A bagger would do everything in parallel and look at all these ensemble models together and see which one has the smallest Gini impurity, which means that the model is learning more effectively and making more accurate predictions, right? So we're looking at the boosting model here. The interpretation is basically looking at customer lag hours, 30 days ratio, like how many returns are you doing within 30 days? Are you doing any returns within 30 days? This would be just one return, repetitive abuse, right? These are things that we need to be aware of. Let me go ahead and create a network graph now to visually try to identify fraudsters. So like I explained before, this is very complex, right? It could be a network of people that are doing buy-sell transactions or buy-return transactions, right? Sending off items, doing handoffs to their friends in this fraud network. They take it maybe to another part of town, maybe even to another city where there's not such a high elevated awareness of suspicion, right? So maybe you can do a handoff to a friend, they drive to another city close by, another part of town, do the returns in a different store, right? And that retailer hasn't even seen that person, and it's a totally different outlet too, so the return might be easier just to get away with. So we're looking at a few different things here: the kind of return, the label, is this potential fraud, yes or no, and the fraud neighbor degree. So these are all the transactions between all the different participants here, buying and selling, returning, not selling, buying and returning, and trying to create the perception of deception, right? So you can't really tell, is this fraud or not? You just give the person the money back when they present a receipt, no questions asked. So in the middle, you can see right here is fraud. This is kind of like the epicenter of all the fraud. You can see this is the network graph here. So here in the middle is the whole fraud ring, right? And on the outskirts here is all the people participating in this fraudulent activity. So if is fraud node 1, if that's positive, this looks like fraud. We can tell by the SKU number, SKU 226. This is something we have to be aware of. So this is SKU 528. So again, like I said, have a system on GCP, Azure, AWS running 24/7, real time, scan the receipt, right? If these items look like they could be flagged as fraud, you have to question the integrity of the return and the person making this return, and maybe call up the store security or something. Double validate, triple validate, try to save the retailer some money, because this is a big hassle. You're making returns for items that don't match your receipt. You're returning more money than the person paid for the cheaper item because they switched it, something like that, right? So this shows us all the relationships. So this is pretty cool kind of graph. And basically what we're seeing here, the red nodes represent customers, okay? Meaning there could be fraudulent or suspicious activities among any customer, but you have to look for those relationships too, right? And trying to determine what is the intention of this fraud, just to get your money back for the actual item that you actually bought, and you change your mind, that's totally fine. If there's anything else, well, maybe it doesn't fit, that's fine too. Anything else that is sus, right? That's suspicious. Like we have to look into this. We have to block it and prevent these returns from occurring. So blue represents items and SKU numbers. So these are products linked to the transaction. Green nodes represent the devices, right? So what kind of device was used to make this transaction? This looks like, customer transaction is fraud, most likely. Fraud neighbor 41 degrees. And And we have the label with no SKU number. That's interesting. Okay, so um, okay, here we have the SKU. So that is the item. Okay, so these are the people over here, and these are the credit cards. SKU is going to have an SKU number. All right, so anything SKU is going to be a number, and anything orange is going to be a card. Okay, so that's indicated down here. Red is customer, blue is the item, SKU number. We just saw that. Green is device, purple is the address, orange is the card. All right, so Visa, MasterCard, you can see that over here. These are card IDs. Each one is unique, hopefully. And what else? And the last thing, gray are the lines or the edges that connect all these relationships. All right, so hopefully that makes sense. If not, Google it. Talk to Chat GPT. If you have questions, you can post it in the comments section. I'll try to answer your questions. A lot of times, though, you can get questions much faster than me answering, responding to questions if you consult with ChatGPT or Google. So one more way of creating this graph network and plotting the results, we can look at kinds labels as fraud, fraud neighbors, and then fraud edges. These are all the connections between all the nodes. Let me control enter to run this, and we can see a slightly different view, more pronounced now for actual fraud. So the darker red color, the burgundy that looks like red wine, these are the fraudulent activities. Any kind of link between this is showing the epicenter or like the fraud network, right? This is a connection of really unscrupulous people that are making fraudulent return transactions, right? So this is the center, and these are all the sort of accomplices all over the place, right? And again, the SKU number is the item number, and anything like this is a credit card transaction, right? And we can change the hop radius. The hop is moving from 1 to 2 to 3 or more different individuals, right? They can um, move these items among a bunch of different people, right? And try to confuse the retail outlet about what's really happening right here. And this is the minimum degree of the connection between the fraudsters, right? So you can change this to look for different relationships or different patterns here in the network graph. Refresh this thing here. Oh, this is different. It's not Plotly. Okay, so I have to refresh this. Okay, got it. So when you see the big red central nodes, this is like a network of fraudsters, right? Dark leaves means you're looking at fraud-centered neighborhoods. The center is the large red node. These are all the fraud customers, again, congregating, getting together, and trying to beat the system. Dark red shows the neighbors, high fraud exposure. Red edges show direct ties to fraud nodes, and then pale nodes are gray edges. When they appear higher, the radius or the degree of threshold is lower. Okay, so it's more of a peripheral kind of contextual relationship between the fraudsters and the retail items that are being returned to the stores um, that that are triggering these fraudulent red flags to be triggered. Right. Okay, so let me scroll down here and we'll finish it up. We're at 43 minutes. It's kind of on the long side of things, but let me jump to the finish line now. Okay, so we're coming up on almost 45 minutes. I'm going to wrap this up. This was kind of on the longer side of things. I want to get this over and done with. I don't want to suck up too much time here, but I think we explored some very interesting topics, and I think this was very enlightening and very informative too. So at the end here, we have some pretty interesting graphs. We can see the whole network of all these fraudulent activities over here. Oh, disappeared. Okay, give me a chance here to refresh this thing. This happens a lot. This happens way too much. Okay, save it, refresh it. Just want to show you those two graphs. I mean, I think you know what it is, right? The network graphs. So go down here, boom, 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 boom. There's my other graphs, right? Frequencies and day of week. And this is feature importance. So that was very useful. Okay, here is the fraud activities and the network graph. So you can see the connections and the relationships between everything. Okay, give it a second to refresh here. Come on. You can do it. I know you're slow. I know you can do it though. Why? Let me just refresh this thing. Come on. Sometimes it just goes so slow. It is it's painful here. Okay, so we have the network graphs, the original. This is focused much more on the fraudulent activities. Darker color is more associated, strongly correlated or associated with fraud. So let me go ahead and print out the actual fraudulent customers, potential customers that are fraudulent, right? So if you see this ID, again, you have GCP, you have Azure, AWS, or Kafka running in real time. You scan the return item. If this customer ID pops up, don't make the return. Okay, that's as easy as that. These are fraudulent customers. We know 61 people are on the do not do business with, do not sell to list, do not refund list, whatever you want to call it. Do not refund list, not refund list, DNRF. Put them on a DNRF list or whatever you want to do. Don't do transactions with these people. This is almost guaranteed fraud. Your business is losing money. We have the top 61, 5 columns. So these are the 5 columns, 61 rows. Okay, so everything is in columns, comma, rows. Excel works the same. It's always column, comma, row. Those are the customers. These are top fraud items. If you see a SKU number 41074 293 all the way down to 195241, don't do the returns on these items. This is 100% fraud, right? Whatever this item is, I don't have the SKU ID converter or translator or mapper. I don't know what that is, but scan the ticket or scan the receipt, whatever. If this person's ID matches up in this first column, don't do the return. Call security or whatever you have to do. If the item ID pops up, don't do the return. Do what you have to do. Don't engage with these people, right? That's guaranteed fraud. So basically, in this exercise, you saw typical signals why people do returns, right? To try to make money, to take advantage of, a quick buck, make a quick buck here. Short purchase return, latency, full refunds on high dollar items, no receipt or lost receipt, right? Making up excuses, receipt swapping, things like this. High return frequency, if you're doing a lot of returns in a short period of time, very sus, right? Very suspicious. Shared devices, addresses, right? If people share the same cell phone, the same address, that's totally sus, right? Like, who is even doing that? That's legit. Nobody, right? Nobody. Many distinct customers tied to one device. Again, shared devices, shared credit cards, shared addresses. That's a no-go. That doesn't make any sense. Refunds to different payment instruments other than what was purchased. That sounds weird. Just don't do that, guys. Don't do that if you work in a retail business. And high fraction of returns versus purchases. So that should be obvious. I mean, I don't think you could return 10 items if you bought 1 or 2. But if somebody is trying to do that, that's clear abuse of the system, and just deny it, right? Just shut that down. Guaranteed fraud. Don't even engage with the person, okay? So that's it. I'm going to wrap it up. We're at 47 minutes, almost 48 here. I'm going to wrap it up. Thanks for your time. Thanks for sticking through to the end. Hopefully this was informative, entertaining, engaging, and what else? Useful, good use of your time. That's it. I'm going to wrap up. I'll post a video later today, and I'll see you guys in the next video when I post that, which will be pretty soon here. Okay, so stay tuned. Thanks. Bye.